Okay. Hi, everybody. This is the second lecture in linear and nonlinear regression topic. In the previous lecture, I have introduced you with the concept of regression, linear regression, and what do we mean by the best fit, and how we can realize that by using Python or any other language. In this lecture, we are going to work out an example where we find the best coefficients of a linear regression line which fits a given data set. The function which we are going to use is called least squares regression, ordinary least squares regression, OLS. Ordinary least squares regression is an old, tested, and commonly used algorithm. It is Python-based and exists. The OLS, it exists in the stats models library. Stats models library is a library of Python which includes several functions and classes related to statistical analysis and testing and predictions. From stats models, we can call the OLS, and from the OLS, we can also call the fit function. Stats models library it is usually used with SciPy. If you want to know about it, you go to the help here to SciPy reference, and then go to SciPy stats, and here you will find stats models. These models deal with regression, linear models, time series analysis, and other works. You work with stats models with SciPy. If you want to download stats models, I recommend you to work with the Anaconda. I have pressed the Anaconda icon here on the desktop. Now, yes, it is appearing now. It is initializing, as you see. This is a large organization which has hundreds of functions and tools which are using Python. And from there, you can download the libraries of interest. I'll show you now how to find the stats models library, and from there you can install it on your computer and use it in order to call the OLS, ordinary least squares method, and from it you can call also the fit model. Now it is, I think, opening, adding feature channels. It is still loading the applications. And now here it is. You go to the environments here, click it. Here you will see the installed and non-installed software packages. I am interested with the installed. And now the Anaconda will show you all the libraries and the functions and the tools which are installed in my computer. This is a huge source, so it takes some time to show you the results of the search. Now, as you see here with these ticks, all of these software packages are installed and they are arranged alphabetically, and you go to the letter S, stats, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, here S now, stats models, sort, SQ, SV here in this stats models. As you see, the stats models is installed. It is statistical computations and models for use with Python SciPy. So it is installed. I can work with it and there is no problem. Now, when we go back to our work here, we shall at first, of course, import the necessary libraries to work with. And of course, now one of them is stats models, because without it, you cannot get the OLS. But before working with the program directly, I want to brief you with the important steps you need to do so as to carry out the regression activity. So as we have said just now, we have at first to import the stats models library. It is already installed and it could be imported by using the import here keyword. And because we are going to correlate between the inputs and the outputs and to find the relationship between them, so we need to know the input values, which are usually as an array or matrix X, which represents the independent variables, and Y, which is also another array or matrix, which represents the dependent variables. So we have to define these values in a way or another. They could be given to you as a result of experiment, or you can get them from a site. Anyhow, it depends. After that, we need always to introduce this very important step, which is add a constant column to the X matrix. We have an X matrix, we have a Y matrix. To the X matrix, we add a column of ones. It is called a constant column. This is necessary so as to take care of the bias value or intercept value when carrying out regression. This is a very important step to be aware of and to do. Now I shall show you what we mean by that. After calling the constant column, we call the OLS, ordinary least square method or function here, to define the model, and then from it we call the fit function in order to find the values of the coefficients of the linear regression line, and then at the end we have to display the results to show the values of the intercept and the value of the slope of the function. This, please don't feel that this is a very difficult thing to do. It is really very easy. If you implement this sequence once or twice, you will get accustomed to it very easy and you will find no difficulties. In order to understand these steps and to be accustomed to and familiar with it, I shall try to give you another example also about the OLS method. So we firstly import the required necessary libraries. We are going to import pandas as PD. Pandas is a library also of Python, based on Python. It deals with data frames where the data is arranged as rows and columns with indexes and headers. Pandas is a very powerful library, especially in machine learning. We are going to use it here. In this example, I shall show you how we can use it. So it is imported. We are going to plot a graph which shows the initial distribution of the data sets values and also the linear regression result, which is the line overlaid to show how and where it lies and how it is looking like. We import NumPy as NP, and the most important new thing here is the stats models.api as SM. As SM is taken from stats models, SM, shortened form. API is always called from stats models. This is compulsory for us to call or to import stats models. Here I gave you a note here about stats models, which is a Python model that provides classes and functions for estimation of any different statistical models, as well as for conducting statistical tests and statistical data exploration. So now we have imported the libraries which we are going to use. Now we want to define the X and Y arrays which represent the independent and dependent variables. Here we have in my computer a CSV file named Ali. It is in the documents. This is the file path to it. CSV file, comma, separated values. There, the values are separated from each other by commas, and this is usually used in order to make economy in the space of the memory. So we have the path to this file, alias CSV, and we need to read it. So we read the CSV file by read CSV function, read CSV, here underscore CSV function, and we pass to this function the path to that file. And we assign this data, these values to a variable, we call it data. So this is now the data will be brought from the file as CSV, and now it is presented as a framework because we are reading it by using pandas. So it is as a framework. Now, this data, which is the body of the file there, we extract from it the X values and convert them to lists so that we can realize a scatter plot. So we use the function toList, we convert the X values to list, and we call it X. So now we have the array of X values which represent the independent variables. To show you, I have printed X only for the first 5 rows. So here, if you look, this is the first row, index 0, 1, 2, 3, 4. This is the first 5 rows, and this is the X values here in the data. If I print X only, here it is 77, 21, 22, 20, 36, up to the first 5 values. And the same thing I have done for Y to show you how they are. But they are, of course, not only 5, they are 300 values. So again, we have defined the X value. We have extracted from the data the Y and converted the Y through toList to a list of Y, and we have also printed the first 5 values of the Y dependent variable. Now we have X and Y as lists, so we can directly use the PLT from Matplot library, the PLT we call scatter plot, and pass there the X and Y arrays in order to plot it. Now here we have plotted all the points of the data set. If you consider it, if you look at it, you will see these blue points which represent the real data set. And as you see, really, it is tending to be somehow linearly rising with a given slope. Now we have defined the X independent variables, and we have defined the Y dependent variables, and we have plotted the scatter plot using X and Y. The third step, as I said, we need to add a constant to the X column. So SM add constant, this is a function, to X. And I have printed for you the first 7 rows of this X to show you what's going there, what will happen to them. If you look at X here, you see 77, 21, this is the column, 22, 20, 36. Now, what I have done with this adding, 77 with added 1, 21 with added 1 column with 1s added to against each value of X. This is the first 7 values of X. Of course, there are 300, but I have shown you only 7 in order to show you a compact and to make economy in the space. So now we have carried out this step by calling the add constant of x, and now we have a new value of x. Now we have already imported SM. From SM we call OLS, ordinary least squares method, and to this method we pass the y and x values which are going to be used, and from the OLS we call the fit function, which is going to decide the values of intercept and the value of the slope. So we have the result. Now the result here really represents all the information which, or includes, let me say, includes all the information which we need to get. Here we are mostly interested to have the values of the intercept and the value of the slope. In order to, for this specific tool, which is OLS here, it is really worked out completely by using different statistical methods, and you can call from the result summary, result.summary function, and as a result of that, you will get a table. It is called the summary table. This summary table is a standard for this function, and it looks like this. This is the summary, and this is the table which I am talking about. This table includes a lot of information. You may need some of it for other tasks, but for now, what we are interested really is in two values, which is the intercept here, which is here given as minus 0.4618 under the title of coefficients, and the slope, which is 1.0143. This is the values of interest for us now. Other values are not for interest, but I can give you an idea about what is going there. Here in this square, practically you have some specifications of the same method. Dependent variable here is y. The model we are using, OLS. The method, which we have called least squares. The date is 30 of July, which is today. Time, it is the time given. Number of observations is the number of points which are given in X and Y. DF residuals represents the actual points which are plotted and used, and so on. R squared here is really of a great importance, which gives you an idea about the accuracy of the linear regression function. Of course, you have other values here related to probability and to other maybe activities which are not required by us. But for those who are interested, or maybe you will be interested in revealing exactly what each of these elements means and what it denotes, I gave you a reference here. I hope that it is given. Yes, this is a reference called Stats Models Regression Summary. This is a title, will never intimidate you again. The stats model summary guide you always wanted to read. This is the name of the author. So you can refer to this resource, and you can read more about the table summary and what each element denotes and what is the information is there. But as you have told you now, for us now, we are only interested in the regression, linear regression value. This is the intercept value and the slope value. And also really we are interested to see what is the accuracy obtained when using this method. It is really very high accuracy. As you approach the value of 1, you are more accurate. Here, as you see, it is 0.989, about 99%, which means very high accuracy. So now we are here. We have printed from the result, we have called the summary, and we have printed the summary as you have seen there. Now we want to draw the linear regression or the line of regression. We have to define the x values, and then we have to define the y function, which is a function of x, because it is a dependent variable. For x, we have the data. As you remember, this is the data which we have already found by using pandas read CSV. We have the data. So data of x maximum function. In other words, we find the maximum value of x. Maximum underscore x means we found the maximum value of x. We found the minimum value of x. Now we have two values, the limits, the maximum and the minimum, the range. And now we can use this range, minimum of x and maximum of x, with a given step I. We can use NPA range and assign it to a variable x. What we have done here, we have created an array beginning from the minimum value of x and ending with the maximum value of x with a step value equal to 1. So now we have an array of values x, and now which is called here x. Now if we multiply this x with the slope, which we have found in the table in the result, and add to it the intercept, we find y. Here it is negative because the coefficient which we have found is here negative, minus 0.4618. So this is the equation which represents every value of y for every input value x. And now we can plot this y by using the plot instruction. We call plot function, introduce there y, and we give it a red color. And at the end, PLT show. So when we run the program, now we shall have this line, which is y, with a red color. And as you see, really, it represents the best fit because it has the best slope and the best value of intercept. As you see, the work is done here. It is clear step by step. You have not to think anymore about different details, and all the necessary activities I have been explained to you without any loss of information. Okay, now we have solved this question by using Python. I want today to solve to you the same question with the same values by using LabVIEW. So let us go out from here and go to LabVIEW to demonstrate to you how we can solve the same example by using LabVIEW. As I told you, in LabVIEW, it is arranged in a way so that you can directly go to the palette of interest here. If we go to the block diagram here, and I have right-clicked here, and as you see, I go to the mathematics, and here the function, the palette of fitting, and here you will find a high number of different programs, which is called VIs in LabVIEW, which could be used for making fitting. Today we shall work with linear fit, and we shall work with another advanced fitting function, which is called, let me say, linear fit coefficients. What is the difference between both? No serious difference. The linear fit coefficients is only, it is this linear fit coefficients VI or program. It is a program simply used for the sake of only finding the slope and finding the intercept values. This is the reason why I use it. But if you need to have more information, suppose you need the values of the regression line. Here you cannot see it. It is not existing. For this sake, I am using here this linear fit VI, linear fit virtual instrument. This linear fit virtual instrument differs from the above one in that it gives you the slope, it gives you the intercept, but also it gives you here at the output an array which represents the best linear fit. So here, this is the array. If I double click it here, you will find the best linear fit. If I take it away here, and you will see 300 values which represent this best fit here. Now, what I have done. At first, you remember in Python, the data which we have worked it was saved in the documents. Here, in order to work with it and to extract from it the value of X array and the values of the Y array, this is the independent variables, and these are the dependent variables, we need to use Read Delimited Spreadsheet.VI. This sub-VI or VI exists in the file input-output here, file input-output, and you find here Read Delimited Spreadsheet.VI. This is the VI which is here. Look at the glasses here, which reminds you that this is a reading function. So what I have done, I have connected this terminal to a path constant, and this path here, which is C users del documents ali CSV. So in the documents, I have a file called Ali CSV. This path now, which is connected, and this file, which is now connected to this function, and at the output, it will give you all the rows of the function. So if you double click at all the rows, you will see these values, X and Y, beginning from 0, 77, 20Y, 1, 22, 20, and until you go to the 300 values, and downwards 300 values. Of course, how I know there are 300 values, it is not that difficult, because I can use array size, index array size here. I put array size here. I connect the array at the output with it. And I now get here the size, create indicator. This indicator now, if I run the program, again, let me see where it is. Here it is the size. Good place for it against the address. So if I run it, it is 301. Why 1? Because it begins from 0 and not from 1. Here 300 rows and 2 columns. 300, this is 1 column, this is the second column. The third column is empty, there is no other values. So the size of this array is 300 rows. Of course, if I go down, this is the size. It gives you only the size. It doesn't give you the values. Okay, here the values are indeed. So when we go back to our case, so we have read all the values as X and Y. Now I want to extract from this array the first column, which represents the X values, and the second column, which represents the Y values. The X values here in this column are indexed with 0, 0 column, and this is the first column. So I use the index array. Here, I go to the array. Here is the index array. I expand it. Now this is the index of X. This is the index of Y. So I am working with the index of Y, 0 and 1. So here is I am connecting this terminal index column to 0, which is this column, and this index column to 1, which is these values. So now at the output, I get this array, which represents the independent variables X. They are going down up to 300 values, and this Y value, which represents the Y values also up to 300. So I have extracted the X values and the Y values. I have defined, in other ways, the X and Y variables. And now I shall use these values to work with this function, linear fit coefficients.VI. It is required to connect the Y. Here is the Y, and the X, here is the X only. You have to suggest the tolerance which satisfies you. This is the tolerance required, which is very high. And the method which is going to be used, least squares, the same as OLS. Now, if I run the program, I shall get the slope and I shall get the intercept. If I look at the results here, the slope 1.014, this is the slope, and the intercept minus 0.455. Remember the values which we have got with you when using Python. Here it was minus 0.46, and here is 1.03. They are practically the same. These values we get here, and we are now satisfied. But I want to draw the linear regression line and to show how it lines really or overlaid on the data set itself, the scatter plot. So at first I want to plot the scatter plot. X, I know X and I know Y. So what I do, let me write it to you. Sorry. Okay. This is a bundle function. I bundle the X and the Y. Now this is the output of the bundle function. And here is the indicator, which is XY graph. I go here, as you remember, to the graph, sorry, here, I go to the graph XY and put it on the front panel. Now this will have a terminal at the block diagram, here, the terminal. But I don't need it here. I just wanted to show you. So I take it away. So this is the terminal XY, which represents the scatter plot. Here it is. These are the points which are 300. Look how they are overlaid over each other because they are very close to each other. And really we have seen a similar picture when used Python. The number of points is very long, 300. Now we want to overlay the regression line over it, so we need to draw the line itself. So for that, we have to take the values of the output of the linear Fit.VI. This is the Y now, the Y values with hat, which represent the predicted values. So they are taken at the input of the bundle function here. And this is the X value again. Here X now, and this is the real value. At the output, we have this output cluster, which represents the the approximated or the predicted value. And now this output here also, which is at the X at Y, is that scatter plot values. I have combined them with an array VI, and the XY now graph will contain both the original scatter plot with the new, which is shown with red, which represents the linear regression line. So as you see now, also, if we go back and look at the output of the linear Fit.VI as a slope value and the intercept value, they are given slope 2 and intercept 2 because we have found the first value by using this function. Here they are, slope 2 and intercept 2. You find that exactly they are the same. So using this function or using this function, exactly, it doesn't matter. The difference only is I cannot make use of the values of the regression line here. So I use this value so that I can plot the regression line. One also interesting thing to do, I want to see the accuracy, the goodness of the regression function. What is the goodness of the fittings which I am now working with? For this purpose, here we have this function where you have as input the XY, the true XY of the scatter plot, and here you have the hat XY, which is at the output here. And we compare them here and get at the output the R square, which we have got before by using the OLS. If you look at it here, you will find it exactly the same value as we have got when using OLS method of Python, 989, remember, and there it was 989. So practically we are getting the same answers Logically, we are implementing the same steps. In the first case, we have used only Python. In the second case, we have used LabVIEW. I don't know which one of them is more interesting for you. I leave this for you, but anyhow, I shall continue my work when demonstrating all the examples to you by using both languages so that you feel confident and you have more choice to select either Python or LabVIEW. Okay, with this, now I finish this lecture. I think it was very useful and fruitful. And in the next lecture, we shall continue with another example using Python and using LabVIEW. Thank you for listening. Wishing you the best.